It's quite classic. It's been studied for a great long time, the effects of immunosuppression. But nonetheless, is it an acceptable risk? That's for the MDs and the patients to decide. And this is a tremendous hurdle, one that I came to love and hate. For example, with the motor neuron treatment, it took us 8 months of design with 4 different people making $500 an hour over hundreds of hours to design this, what's called the pivotal preclinical safety study. It's 6 months in duration, and it tests biodistribution. You don't want the cells to get out before you put them. Tumorigenesis, of course, because they were derived from HESCs. Toxicology in blood and urine, all the med chem, and pain assessment. It must be outsourced. The FDA requires it to be outsourced to a GLP facility. So that $750,000 price tag we had to endure was not easy to swallow. How does an academic laboratory do that? Well, we didn't. We had to go to industry to get that money. We had to go to foundations and launch a tremendous amount of effort to raise that, because these people are in business to make money that run GLP facilities, and they need to be paid. There are actually over about 180 outcome measures and time points over 6 to 12 months. That's not trivial. I don't know how to do those things, and I bet there's nobody in this room that knows how to do them all. My point here is that it's extraordinarily expensive and extraordinarily specialized. These things are, we are inadequate as a spinal cord research community to address these things. So it takes a great deal of cooperation. 8 months of planning, 6 months of duration, 180 or so outcome measures. This is no small task, and it's something that has only happened twice in the United States. Whether large animals have to be used is really, these are the sort of the guiding principles that I've used for determining this. One, what's the validity of the existing models? Is there a good monkey model of contusion spinal cord injury? No. There's a great model that's being developed for hemisection and laceration injury, but is there one for contusion? And I know you don't go to the monkeys in order to try efficacy. You're doing it for safety. But shouldn't safety be evaluated in the injury model that we're addressing? Because isn't spinal cord injury, so says Lynn Weaver, and I believe her, and I think everybody does, associated with inflammation in virtually every organ in your body? So it does make sense that we go into valid animal models. Not to test efficacy, but we're still testing safety. But it is important that we don't put these things in healthy, normal monkeys. What we're going to get out of that is, in my view, useless in interpretation of the safety of that product. It must be confounded, influenced by the environment of an injury site, a contusion. And if we don't have a valid model, then how good is that model? What, is it worth going to? Whatever model you have, is it adequately characterized? You know, when I almost put my oligodendrocyte preparation with Jeff Kosis and Tajinski, and we were sitting planning putting these things into the monkey model, we were all happy about it. Everybody wanted to do it. We said, let's put the oligodendrocyte progenitors into the laceration model because it is validated, it's characterized, let's go. So we got together $3 million in order to run the trial, no small feat, and all the credit to Jeff. And then I said, wait, this is a laceration injury. Maybe I should take a look and see how much demyelination there is in laceration injury. And sure enough, there isn't. There's virtually no demyelination in a laceration injury. This is actually a lacerated spinal cord 24 millimeters away from the site. You can't even see anything there. And so I published all that stuff in rodent models saying that a laceration is not a contusion injury. But the moral of the story there is you have to be model specific. You've got to validate and characterize your model before moving forward. That does not exist in the monkey field yet. So that's not a defense saying we shouldn't go to monkeys. I think that's tremendously powerful and very valid approach, but not all the time. The cost is tremendous. The skill set required is not to be underestimated. We should always think about the ethics of using these sentient beings. And the necessity, here's one of my major points. The necessity is not dictated by a list. It's biology. It's the transplant population. And this issue should never be generalized. Do you use monkeys or do you don't? It is foolish and immature to say, yes, you should always use them, or no, you should not. They are treatment specific. So the oligodendrocyte story, for example, I would argue that why would you go to monkeys in that model? The way that one cell myelinates an axon of any species is the same regardless. We've had monkey cells myelinating virtually every vertebrate and human cells myelinating every vertebrate, so what's different there? It's the biology says, why would you need a larger animal? Whereas a motor neuron, for example, now you've got a size issue. There's more reason to do it in that model because the distance from my thumb to my spinal cord is a heck of a lot longer, and then that cell is expected to do, and it has to interact with all of the things along the way, immune responses, etc. So it has to be analyzed per treatment and never generalized. The instrumentation, I don't have much to say here because I honestly don't know much about it, but I just know that it's a big scary subject. Instrumentation, medical device, is usually the stuff of an entire company. So for a small company to go out and develop instrumentation is a mammoth undertaking. We don't know what we're doing. That's one of my major points here. We are not the ones to be developing instrumentation alone. We need experts in the field, engineers who are good at that. And take a look sometime, jump onto a medical device company and look at their skill sets, and you will see that yours is rarely represented. They're very, very unique. The cost is prohibitive. When you do have some gear, you then have to revalidate all of your work. So for example, this is just one slide I pulled out of the motor neuron program where we had these little microspheres, right, we're growing up, and as you grow them over time, they get bigger. But the transplant device that we've developed can only put in cells that are so big. So after speaking with the FDA, we actually had to go revalidate. This is one slide of about 80 of the amount of the verification of this approach that we had to do in order to show that we have 22 hours to prepare our cell population before transplant. And at 22 hours, it's called your batch release criteria. It ends. Boom. The cells are no longer any good. So from the time we begin to prepare these cells for transplant in a human or in a rodent, we have 22 hours, otherwise the cells just get too large. And this is complemented, of course, by a lot of data on their survival. Manufacturing and qualification of the cells. That's another thing. This slide addresses QA/QC, quality assurance, quality control, which I know very few laboratories that actually have QA/QC departments. And so in a preparation, say, of motor neurons, we do some cell expansions, and then we differentiate a non-adherent, and then we put them on adherent, and we make microspheres, and we deliver them and transplant them. So that's the process. But while we're growing them, we have to make media and substrate and manufacturing the HESC media, not only the HESC, but the motor neuron media. They have to be in an independent media QA/QC testing facility. Not the same one, has to be different than this testing facility down here that batch controls and batch releases for all of these steps. In addition, with regards to manufacturing and qualification of the cells, it must be GTP. You have to have it scalable. You have to have quality checks, product checks, batch release criteria such as this, and here's a big one. You have to go and repeat everything that you've ever done using your final formulation once you've done all this. And I know one company who spent $17 million putting that together, another that spent $3 million putting that together, in order to generate what's called a final formulation. And then you have to realize that all of that animal work, your 2 guys in a rat story that was marvelous, is irrelevant. You have to repeat it all using the final formulation from your GTP. So if you do not pay attention to this type of thing while you're thinking about translation, then you must realize that everything you're doing is irrelevant to clinical translation. Absolutely irrelevant. You can't go to the FDA, 2 guys in a rat, and say, I made a rat walk again. They say, great. Make the cells in a clinically compliant manner, then come on back, do it all over again, and show us that your final formulation, because it's a different product than I'm growing in my lab at UCI and Scott's growing in his, and Steve's growing in his. It's a different product, and it has to be scaled. It can't just be that you make it QA/QC. You have to make it in precisely the same manner that you're going to make it for when you address humans. So you have to then do a market analysis and anticipate that you're going to treat 2,400 patients a year and build a production facility that can handle that, just so that you can go do all of your preclinical animal studies. That's quite a barrier. So here